So this is the second video on the geometrical significance of determinants. So in the previous video, we talked about the fact that the size of the determinant, so that example that we did, showed that if you take the determinant and you work it out, its size gives you the area scale factor of the transformation that the matrix represents. But I said the word size deliberately because sometimes determinants can be negative, for example. So if we look at this matrix here, M, which is 1, 4, again just reading the columns 3, 2, you can see that if you take the determinant of M, it's going to be 2 times 1, or 1 times 2, minus 4 times 3. So we're going to get a determinant of minus 10. So then the question is, well, what does that mean? What does it represent? So if we think about the same situation we had before, and again, the scale on this is just going to be 1 square to 1 unit because it's a little more difficult to fit on this time. So just 1, 2, 3, 4, 1, 2, 3, 4, and so on. So if we think about a unit square again, let's start by thinking about just the I vector, the little line that goes from 0 to A. So this one here. So the image of this little vector is going to be 1, 4. So in other words, this point here, A, is going to end up, well, 1 across and 4 up. It's going to match with that point there, which I'm going to mark as A dashed. And if we take the vertical vector, or the little vector that goes from O to C, or the point 0, 1, well, that's going to be mapped to 3, 2. In other words, it's going to be mapped to this point over here, C dashed. And in the same way, when we work out what B is, it's going to be up here. It's going to be the sum total of those two vectors. So outwardly, at a glance, it looks like not much has changed. It looks like you've got a unit square. It looks like if you work out the new shape, the parallelogram that it ends up being turned into, it looks pretty much like the last one. And if we worked out the area, well, I'm going to tell you now, the area of this thing would be equal to 10. But notice something has changed. The orientation of the shape has changed. Because this time, instead of going O to A to B to C, kind of going round anti-clockwise, the way that I've labelled the diagram, the new parallelogram goes O to A dash to B dash to C dashed. Because the image of O to A ended up being kind of above the image of O to C dashed. Now, again, we could do all this in the abstract. We could do with A, B, C and D's, and we could prove all of this, but it doesn't really add a lot of light to the situation. It's exactly the same thing that's going on, which is that if you get a determinant, which is positive or negative, it doesn't matter. The overall size, so I'm going to write the modulus of the determinant is always equal to the area scale factor of the transformation. So this is minus 10 for the determinant. The modulus of that is 10, and that's going to be the area scale factor. But the negative does give you some more information. So when you see a negative determinant, what it means is the orientation of the shape has changed. So instead of, if you had the shape labelled, for example, anti-clockwise, it'll now be labelled clockwise. And vice versa. If you labelled the old shape clockwise, if I had labelled this one O, A, B, C, well, the new shape would be the other way around. So you get a little bit of extra information, but again, the modulus tells you the actual area scale factor. There's another possibility, because in this case, we had a negative determinant. In this one here, you can see we're going to get a 0 determinant, because again, if I work this out, I'm going to get determinant of M, I'll just write it up here, determinant of M is equal to 6 minus 6, which is 0, like that. So then, what does that mean? Well, we know that, that's called dropping my pen. So we know that, first of all, when you've got a 0 determinant, it means there's no inverse. So what's going on here is you've got lots of points that are probably being transformed into a single point. It's not like a nice neat shape that's being rotated. If we look at the columns, we can understand this almost straight away. Because what's happening is this vector here, this little journey from 0 to 1, is being transformed into the little journey from 0 to 2. This vector here, from 0 to 1 vertically, is being transformed into the vector 3, 6. And in fact, what that means is every single point, no matter which point you choose on the plane, all of them are going to be transformed so as to lie on this line. I mean, that's kind of intuitive, but we can do it a little bit more algebraically if you like, if I do this. So if I take my just general point and I multiply that matrix by a general point, I'm going to get a resultant matrix, which is going to be x plus 3y, 2x plus 6y, and that's going to equal the image point. But you can see pretty much straight away that double the x coordinate for the image points is the y coordinate for the image points. So in other words, for every single image point, y dash is equal to 2x dash. In other words, all of the points are being mapped onto some point on the line y is equal to 2x. Don't know whereabouts that will be, we'd have to work it out. But every point on the plane, you choose a point on here, they're all being mapped onto the point y is equal to 2x. Okay, so if we just take this idea a little bit further, so this situation where you've got points being mapped onto a single point, and maybe look at the next example. So in this example, we're looking at the same idea, the same matrix. We've got m equal to 1, 2, 3, 6. We know that all the points in the plane are being mapped onto the line. Again, y is equal to 2x. But say I choose one of those points. It doesn't matter which one, but say I choose, just for simplicity, 1, 2. And I want to know which points are being mapped onto 1, 2. So all the points in the plane, which points end up being transformed into 1, 2. So I can also do that. I can also work backwards and work that out. So I'm going to get 1, 2, 3, 6 multiplied by some point xy gives me 1, 2. If I multiply this out, I get x plus 3y is equal to 1 from the first line of the multiplication. I get 2x plus 6y is equal to 2. Okay, well that's the same equation, just doubled. And what this is telling me is, if you think about any point that lies on x plus 3y equals 1, so this whole line of points that we could draw on here, so this is going to be the same as y is equal to minus 1/3 x plus 1/3, just to help us kind of visualize it. So you can imagine you've got this line minus 1/3 x plus 1/3, some kind of pretty shallow line going down like this. Probably a terrible diagram, but you get the idea. All of the points on that line will end up mapping to that point there. So it's not quite like a projection that we saw last time when we first saw determinants equal to 0 and talked about the fact they don't have an inverse. There is a line of points that's mapping to the point 1, 2, but they're all of the points that lie on that particular line. So we know what the points are, but also we can see there's going to be no inverse, because if I chose a point on this line that gets transformed to 1, 2, you've got no way of telling me which precise point I would have transformed to 1, 2. You only know the line of points that it could have come from.